In order to describe the behavior of real gases in thermodynamics, we start with the ideal model describing the behavior of gases, that is, with the ideal gas law. When we combined Boyle's law, Charles's law and Gay-Lussac's law into one formula, we obtained the ideal gas law describing the equation of state for n-mole ideal gas occupying the volume V at the pressure P and the absolute temperature T, which is the following. The pressure P times the volume V is equal to the amount N of the gas, times the universal gas constant R, times the absolute temperature T. We also showed that how the three gas laws arise as special cases of the combined gas law. In the case of isothermal processes where the gas temperature is constant, we obtain Boyle's law stating that the pressure P times the volume V is constant. We also plotted a family of isotherms for given temperatures T1, T2, T3 and so on in the pressure versus volume diagram of the gas, which are hyperbolas. The range of validity of the ideal gas law with respect to the behavior of real gases was represented by a color gradient in the diagram. Over the area of the lower pressure range, the transition from dark green to a brighter shade indicates that the ideal gas law gives more accurate approximation for dilute gases, that is for low density and low pressure. In the case of isobaric processes, the gas pressure P is constant, and we saw that the volume V of the gas is proportional to its absolute temperature T, which is Charles's law. This form of the law shows the advantage of the absolute temperature scale over the other scales of temperatures, since the actual volume of the ideal gas is directly proportional to the gas temperature measured in Kelvin. Here no reference volume is needed to formulate the law as opposed to the case where the temperature is measured in Celsius. The isobars in the volume versus temperature plot consist of a family of lines starting from the origins of the axes, which represent the absolute zero and a vanishing volume. The tangent of each isobar depends on the given values P1, P2 and so on of the gas pressure. At low temperatures the gas law is not valid, since the volume of an ideal gas shrinks to zero when we cool it down to absolute zero. The condensation of real gases shows that we cannot use the equation of state for an ideal gas at low temperatures. The law gives a good approximation only at higher temperatures indicated by the bright green area in the diagram. In the case of isochoric processes where the volume V of the gas is constant, we found that its pressure P is proportional to its absolute temperature T formulated in Gay-Lussac's law. Here we also saw that the gas pressure is directly proportional to the temperature given in Kelvin, and we do not need to apply any reference pressure measured at a given temperature as in the case of the Celsius scale. The isochores in the pressure versus temperature plot consist of a family of lines starting from the origins of the plot, which represent the absolute zero and a perfect vacuum. The tangent of each isochores depends on the given values V1, V2 and so on of the volume of the gas. According to this law, the pressure of the gas also vanishes at absolute zero, which is not the case in nature due to the condensation of gases. This law only gives a good approximation at high temperatures and low pressure indicated by the bright green area in the middle right side of the diagram. These findings related to the range of validity of the three gas laws and its combined form in the ideal gas law follow from the study of the behavior of real gases. When we compare this behavior, that is the relation between the pressure, volume and temperature of a given amount of real gas with predictions given by the equation of state of an ideal gas, we will find the deviations from the behavior of an ideal gas presented here. Then we need to describe this deviation quantitatively, and draw some conclusion from the results that could help to construct a better model with new equations of state describing the behavior of real gases more adequately. In order to describe this deviation quantitatively, we will introduce the compressibility factor of real gases as follows. We have seen that the behavior of real gases often deviate from the behavior of an ideal gas, that is the observed or measured relationships between the state variables of a real gas, that is its volume, pressure and temperature are not accurately described by the ideal gas law. The form of the ideal gas law can be simplified if we define the molar volume Vm of n mole gas by the ratio of its volume V to n with the unit or cubic meter per mole. Then we measure the deviation of the behavior of n mole real gas confined in the volume V at the temperature T and pressure P from the ideal gas law, given by the equation stating P times Vm is equal to the gas constant R times T, by introducing the deviation factor Z of the real gas and write its equation of state in the form stating that P times V is equal to Z times R times T. We call this deviation factor the compressibility factor of the real gas, and it is given by the ratio of the product of the pressure P of the real gas and its molar volume Vm to the product of the gas constant R and the absolute temperature T of the gas, where the pressure, the volume and the temperature are measured for a given amount of real gas. The name compressibility factor indicates that it can be defined for a given real gas as the ratio of the molar volume Vm of the real gas at a given temperature T and pressure P, to the molar volume Vm of an ideal gas at the same temperature T and pressure P, if we divide the equation of state of the real gas by the ideal gas law. We note that the reciprocal of the square root of the compressibility factor Z, known as the supercompressibility factor F for given pressure P and volume V, is also in use. Here we show the compressibility factor of a given amount of gas measured at a given temperature for hydrogen, oxygen, carbon dioxide and methane as a function of gas pressure. By definition, the compressibility factor is equal to 1 for an ideal gas, and as the diagram shows, Z tends to 1 at low pressures for all the types of gases. The very different curves for the deviation factor seen in the diagram also indicate that Z as a function of pressure, density or volume, and temperature must be measured for each type of gas, since it is not a universal function for real gases. We can also see that its value generally increases with pressure and, as we will see, decreases with temperature. Although each type of gas has its own unique compressibility factor represented by the different curves in the diagram, it is possible to give a general description for all gases based on a theorem called the principle of corresponding states. This principle will be presented when we construct a more realistic equation of state for real gases, and we will apply a universal description of the deviation factor as a consequence of the theorem. We will see that such a description provides a general method to determine this factor for each gas from measurements. We present further plots of the compressibility factor of real gases as a function of their pressure for different temperatures based on measurements. We chose 3 types of gas, such as hydrogen, nitrogen and oxygen, plotted for different temperatures between 0 degrees Celsius and 200 degrees Celsius, that is between 273.17 Kelvin and 473.17 Kelvin. The families of the plots for the deviation factor versus pressure measured at constant temperatures are very different for the 3 species, but we can still make some general statements on them. All the 3 diagrams show that the compressibility factor is approximately equal to 1 at low pressures and at high temperatures, and real gases behave as an ideal gas at atmospheric and standard conditions. We can also see in the diagrams of nitrogen and oxygen that at low pressures the volume of a real gas is generally lesser than the volume of an ideal gas at the same pressure and temperature. This property makes a real gas highly compressible at low pressure, that is, the gas can be significantly reduced in volume when subjected to relatively small pressure. This is also true for hydrogen, but this effect can only be observed at temperatures lower than about 200 Kelvin, where the compressibility factor is less than 1 at low pressures. As pressure steadily increases, the deviation factor decreases to a minimum. Again, this effect can be measured for hydrogen at low temperatures as well. The compressibility factor increases above 1 at high pressures and the real gas becomes incompressible, that is, its volume cannot be significantly reduced even if a high pressure is applied on it. We summarize the behavior of real gases over the different regimes in this table. In the first line we show the regime where the compressibility factor is less than 1. By definition, it means that the molar volume Vm of a real gas is less than the molar volume Vm of an ideal gas at the same pressure and temperature. This inequality shows that the product of the pressure P of a real gas and its molar volume Vm is less than the gas constant R times the absolute temperature T of the gas. In the second line of the table we show the case of unit compressibility factor, where the molar volumes of the real and ideal gases are equal at the same pressure and temperature. Then the ideal gas law holds, telling us that the pressure P of the real gas times its molar volume Vm is equal to the gas constant R times its absolute temperature T. Here the ideal gas law gives a good approximation of the equation of state of the real gas. In the third line we consider the case when the compressibility factor is greater than 1, that is, the molar volume Vm of a real gas is greater than the molar volume Vm of an ideal gas at the same pressure and temperature. As a result, the product of the pressure P of the real gas and its molar volume Vm is greater than the product of the gas constant R and its absolute temperature T. The second line of the table indicates that a real gas can behave as an ideal one, where the ideal gas law provides a good description of the relation between its state variables in a given regime of these variables. However, the first and last line together with the plots clearly show that its behavior has a non-negligible deviation from the ideal gas law over a wide range of the state variables. Based on these findings, we conclude that the fundamental assumption made on gases at the beginning of our study on thermodynamics, stating that a gas is a continuous substance, is not tenable, and it cannot be used to completely explain the behavior of real gases. In fact, the idea that a gas is not a mere continuous medium was already shuffled into our discussion when we started to use the amount of matter measured in moles as one of the properties of gases. We established that the unit of mole appearing even in the ideal gas law describes a given amount of gas species measured in the number of particles that form the continuous substance of gases dealt with under standard condition. Then we need to assume that real gases are composed of a large number of very small particles called atoms or molecules that are in constant motion. The distance separating the gas particles is large compared to their size, and these particles in constant motion collide each other in the wall of the container of the gas. We also assume that there is an interaction between the particles colliding with each other, and between the wall and the particles bouncing off the wall. We will apply these assumptions on the discrete nature of real gases and attempt to explain the deviation of their behavior from the behavior of an ideal gas. Apart from the second line in the table describing the case of an ideal gas, we need to interpret the other two cases for real gases. If we consider the regime described in the first line of the table, we see that the volume of a given amount of real gas is smaller than the volume that would be allowed for the same amount of ideal gas at the same pressure and temperature. This indicates that there is an interaction between the gas particles that is attractive in its nature, and the moving atoms or molecules of the gas species pull on each other. This attraction helps the particles get closer together and they occupy a smaller volume than it is expected if the gas were acting as an ideal gas. In the case of the regime described in the third line of the table, the volume of a given amount of real gas is greater than the volume of the same amount of ideal gas at the same pressure and temperature. This effect is explained as follows. As pressure increased, the gas particles are crammed closer and closer together. Because they have a finite size, the atoms or molecules start pushing the other atoms or molecules away harder. As a result, they will occupy greater volume than it is expected if the gas were acting as an ideal gas. Based on the considerations of these effects, a new equation or new equations of state of real gases can be introduced, providing a more adequate description of the behavior of real gases. Before introducing the equation of state for real gases, which will help us to find an efficient method to determine their compressibility factor, we present a simple procedure called Burnett method to measure the deviation factor of real gases. In the measurement we can use an apparatus similar to the one used by Joule in his original experiment on the free expansion of air. As seen in the figure, the apparatus consists of two gas containers which are connected with a tube and placed into a vessel filled with water, serving as a calorimeter. The gas containers are denoted by the letters A and B in the figure. The tube is closed with the valve separating the two containers from each other. The container B has an outlet closed with another valve which is attached to a vacuum pump. The container A of volume VA is filled with a gas at a high pressure P0 and at an absolute temperature T, whereas the container B of volume VB is evacuated. We assume that the whole system is in thermodynamic equilibrium, and we can apply the modified gas law to describe the relationship between the state variables of the gas in the container A. Then we write that the initial pressure P0 of the gas times its volume VI is equal to the compressibility factor Z0 times the amount of species N0 of the gas times the gas constant R times the absolute temperature T of the gas. If we open the valve of the tube connecting the two containers while the valve of the outlet is closed, then we let the gas in the container A expand into the evacuated container B. When Joule performed his experiment, he found the free expansion of air did not change the temperature of the gas, that is, the gas had an isothermal expansion. However, in his experiment the initial pressure of the air was only about 20 bar, where the compressibility factor of real gases is still close to 1, and the ideal gas law provides a satisfying approximation of the behavior of the gas. If the initial pressure P0 is 10 times greater than the pressure applied by Joule, then the behavior of the real gas has a non-negligible deviation from the one predicted by the ideal gas law. In this case we can measure a change in the temperature of the expanding gas, which is an effect characteristic of real gases, and it will be studied after the introduction of a new equation of state for real gases. In this measurement we will wait until the thermostat can equalize the temperature of the expanded gas in the containers at the temperature T. When the thermodynamic equilibrium of the system is achieved, we measure the pressure P1 of the gas, and write its equation of state in the form stating that the pressure P1 times the sum of the volumes VA and VB is equal to the compressibility factor Z1 times the amount of species N0 of the gas times the gas constant R times the temperature T. If we divide the second equation of state by the first one, then we can write the ratio of P1 to P0 times the ratio of the sum of VA and VB to VA as the ratio of Z1 to Z0. As a result, the compressibility factor Z1 in the first step can be expressed by the ratio of the pressure P1 in the first step to the initial pressure P0, times R V times the compressibility factor Z0, where R V is the ratio of the volume expansion of the gas, that is the ratio of the sum of VA and VB to VA. The containers are identical in the figure and they have the same volume, but in practice a Burnett apparatus applies a container B that has a much smaller volume than the container A in order to produce only small changes in the pressure of the gas after its expansion. Then R V is somewhat greater than 1. Now we close the valve connecting the containers and then we open the valve of the outlet of the container B so that we can evacuate the gas from it by using the vacuum pump. After completing the evacuation of the container B and closing the valve of its outlet, we have restored the original condition but with less amount of gas in the container A at a lower pressure at the same temperature. In the second step, we measure the pressure P1 of the gas left in the container A and where the state of the equation of the gas is the following. The pressure P1 of the gas times its volume VA is equal to the compressibility factor Z1 times the amount of species N1 of the gas times the gas constant R times the absolute temperature T of the gas. Now we let the gas in the container A expand into the evacuated container B again by opening the valve of the tube connecting the two containers. We wait until the temperature of the expanded gas reaches the temperature T of thermostat and the system attains thermodynamic equilibrium. Then we can measure the pressure P2 of the expanded gas, and write its equation of state in the form stating that the pressure P2 times the sum of the volumes VA and VB, is equal to the compressibility factor Z2 times the amount of species N1 of the gas times the gas constant of the temperature T. If we divide this equation of state by the one obtained in the previous step, then we can express the compressibility factor Z2 in the same form as in the first step, that is by the ratio of the pressure P2 to the pressure P1, times the ratio of volume expansion RV, times the compressibility factor Z1. By substituting the expression obtained for Z1 in the first step into the right-hand side, we can write it as the ratio of P2 to P1, times RV squared times Z0. In the end of the second step we close the valve separating the containers, open the valve of the outlet of the container B, and evacuate it by using the vacuum pump. Then we can continue the same procedure with the third step. After K steps, we will able to express the compressibility factor Zk by the ratio of the pressure Pk to the initial pressure P0, times the ratio of volume expansion RV to the power of K, times the initial compressibility factor Z0. The right-hand side is equal to Z0 over P0, times RV to K, times Pk. If the ratio of Z0 to P0 is known and the ratio of the volume expansion RV is given by the geometry of the apparatus, then the measurement of the pressure Pk of the gas is enough to calculate the compressibility factor Zk of the gas in the step K. In fact, it may be difficult to determine the exact ratio of volume expansion RV due to the complex internal geometry of the system formed by containers, pipes and valves. However, we can divide the equation of state in the step K by the equation of state in the step K-1 as seen in the first step. If we assume that K is big enough that the pressures Pk-1 and Pk measured in the steps K-1 and K tend to 0, then the compressibility factors Zk-1 and Zk in the equations of state in these two steps tend to 1. As a result, the ratio of volume expansion RV can be written as the limit of the ratio of the pressure Pk-1 to the pressure Pk, where K formally tends to infinity or the pressure tends to 0. In practice, as K increases the ratio Pk-1 to Pk converges to a finite value of RV, and we can stop the measurement process in any step where we reach the demanded accuracy of the ratio of volume expansion. One can use helium gas to evaluate this ratio from the experimental pressure ratio data, since helium with its small atomic volume and weak inter-atom interaction is close to an ideal gas with a unit compressibility factor. Other candidate for this measurement would be hydrogen, but it is far less safe to handle. We still need to know the ratio of Z0 to P0 to determine Zk. If we plot the ratio of volume expansion RV to K times the measured pressure Pk in the step K versus the pressure Pk itself, then we obtain a series of data points. With the increasing number of the steps K, the pressure Pk decreases and the compressibility factor Zk approaches 1. Then the value of RV to K times Pk given by P0 over Z0, times Zk tends to the ratio of the initial pressure P0 to Z0. That is, the fitting line over the data points will intersect the y-axis at value of P0 over Z0. After having determined this value from the graph, we can insert its reciprocal into the right-hand side of the equation describing the compressibility factor Zk. Then the later will be evaluated in any step K, that is for any measured value of the pressure Pk, and we can compile the compressibility factor versus pressure chart of the gas at a given temperature T.